In the last video, I showed you a very simple introductory example, and the conclusion of that example was that there are some algorithmic way to do the same problem. So it's possible to remove the roots, that is the eigenvalues of a system, to a new places. But how to do it in an algorithmic way? In this video, I am going to show you 3 ways. The first way, in the first way, it's a little bit special because we have to use the controllable canonical form. So this is one group where we can use the controllable canonical form. So it's a very good chance if our system is in the canonical form, in the controllable canonical form, but usually it's not the way, because usually we have got a system with A and B. We need A and B now, and there are some transformations. I'm going to speak about this transformation at the end of this video, with which we can get the controllable canonical form A tilde and B tilde. And let's say our system is in the controllable canonical form first. So it's here that we have spoken about some videos before. So the first row of A tilde and B tilde is the minus A1, minus A2, etc. minus AN, and 1 in the B. And the other part below this line is very special, has a very special form. And this is the associated matrix of the following characteristic polynomial, which is an n-order polynomial, lambda to the power of n plus a1, lambda to the power of n minus 1, etc. an. And these coefficients a1, a2, and an appears in the first row of A tilde. And this is the open loop system A. It means that we can calculate lambda 1, lambda 2, etc., lambda n. That is, we can calculate the eigenvalues of the open loop system. But we want to change them because they are too slow, they are not stable, they have sinusoidal transients and so on. So we don't like their behavior. That's why we would like to change lambda 1 to lambda 1 tilde. We want to change lambda 2 to lambda 2 tilde, etc., lambda n to lambda n tilde. And from this closed loop characteristic polynomial, we are going to get the coefficients of p1, p2, and pn. It means that, and I draw it with another color, it means that from the open loop system, we will have a closed loop system, and we would like to change the characteristic polynomial coefficients from a1 to p1, for example, from a2 to p2, etc., from an to pn. And for this p1, p2, and pn coefficients, we will have an associated matrix which we can obtain as follows. This is the closed loop system, A tilde minus B tilde K tilde transpose. And in this, K tilde transpose is not known. We would like to obtain these values in such a way that this matrix A tilde minus B tilde K tilde transpose has the eigenvalues of lambda 1 tilde, lambda 2 tilde, etc., lambda n tilde. So after some very simple math, doing these steps, we are going to get this associated matrix. This is the associated matrix of this polynomial. So we have got this polynomial of the closed loop system, and this is the associated matrix at the end here. So it means that this value a1 plus k1 tilde must be equal to p1. a2 plus K2 tilde must be equal to P2, etc. Because if we go back for a short to the green notations, A1 in the polynomial appears here, A2 in the polynomial appears here in the matrix, and so on. So these values must be exactly the same, and these are what I have copied to this place. So P1 is A1 plus K1 tilde, P2 is equal to A2 plus K2 tilde, and so on. And if we make some vector notations like this, we can get K tilde transpose, which is equal to P transpose minus A transpose. In P transpose, we can collect the coefficients of P1, P2, etc., Pn, and in A matrix vector we can collect A1, A2, etc., An. So in P we have got the desired values, and in A there is the given values. The given values from the open loop system, and in P the desired, which will be the closed loop system. So this is how to get K tilde transpose. It's very simple, because we have to work with the coefficients of the closed loop polynomial and the open polynomial, and we can get the K tilde transpose. Okay, let's go to the vector, so the input of the system, which is u, and it is minus K transpose x. There is no tilde in this case, but it is equal to minus K tilde transpose multiplied by x transpose, because the system input is not changing when we use any kind of coordinate transformation. The first one is minus K transpose x. This is the original system state, x. And in the second, minus K tilde transpose x tilde. In this case, we are working on, don't forget, we are working on the controllable canonical form. And x tilde is equal to t multiplied by x. And with this, we can go back to the original system. And this is what I put to here. So the K transpose is equal to K tilde transpose multiplied by the transformation matrix. And then I put this result back to here. And this is what we really need. So the K transpose is equal to P transpose minus A transpose multiplied by the transformation matrix. And this transformation matrix is appearing here at the top of the page, with which we can realize the controllable canonical form of any system. And this is what I have not shown you before. And at the end of this page, we can conclude that there is a very, very simple way to make the pole placement technique if our system is in the controllable canonical form. If our system is not in the controllable canonical form, we have to use the same result. This is here at the end, but we need some transformation. And this is what we call the Basgura algorithm, or the Basgura method. In the Basgura method, K transpose is calculated by P transpose minus A transpose multiplied by T, and the T is shown here without any proof. So this is the transformation matrix which we can use to transform our system to a controller canonical form. So here we can see MC matrix and the tau matrix, and tau matrix argument is the A vector, and we have to obtain the inverse of this matrix. So here we can have MC inverse. It means that in this equation we have to use the controllability matrix inverse. So our system must be controllable if we want to use this pole placement technique. What is the tau matrix? The tau matrix is a Toeplitz matrix, and this is the definition of the Toeplitz matrix with the coefficients of the open loop system A1, A2, etc. An. So it's very easy to set up. So it's very easy to make the inverse of it, and we have to multiply with the MC inverse, and we can get this transformation matrix here. And this technique is called the Basgura method. Please don't forget there is MC inverse inside the technique, so the system must be controllable. The other one is a very famous formula, the Ackermann formula for the single input, single output systems. And this is the formula: K transpose is equal to a row vector. All the elements are 0, but not the last one, which is equal to 1. So the number of elements here is n. It is multiplied by MC inverse, so the controllability matrix inverse we always again need. And then it is multiplied by the polynomial of the closed loop system, but the argument is not lambda here, not lambda, but the matrix A. What does it mean? It's here. It's quite a tedious work to set up the phi CL polynomial of the matrix A. So this is the matrix which can be calculated as follows: a to the power of n plus p1 multiplied by a to the power of n minus 1, and so on and so on. So it's a matrix again. So we multiply MC inverse in phi CLA, and we have to get the last row of this matrix because of this element here. And I'm going to show you an example how to work with it. If our system is 2 by 2, so the number of the states is equal to 2, so it's quite easy to work with hand. But if the number of the states is larger, 3, 4 or more, by hand it's very difficult, and there are software tools to work with the Ackermann formula, and it's very easy to realize the Basgura method too by a mathematical software.